Here is the question that I ended the first part of this video lecture with. And if you were doing this through Moodle, then you were presented with these 4 options for answers, one of which is a yes, you do just divide the force by the mass, and the other are 3 various no's with various suggestions of what else you might do to get a quantity that's independent of the force of the probe particle. Well, A is clearly not correct. We know that Q2 is bigger than Q1, and that's why the force on Q2 is bigger than the force on Q1, but we know nothing about these masses, and so in general, we certainly don't expect that dividing these forces by the masses would give us the same answer for both probe charges. So A is right out. But I gave you a hint. I said that you know that these forces are determined by Coulomb's law. And so in particular, if the distance out to the point A is given by r, then the force on charge 1 would be this, and the force on charge 2 would be this. And all those absolute values don't matter because I made all of these charges positive, so they're just a distraction. Let's drop the absolute values. And so here are the magnitudes of these 2 forces. In both cases, we know that when we divide either of these force vectors by anything here, any of these charges or masses, we will get a vector that points up, because dividing by a positive scalar won't change the answer. And so we just want them to come out with the same magnitudes. Well, what is the part of the expression for the force that depends on the probe charge? Well, it's just those charges, the Q1 and the Q2. Those are properties of the probe particle. And so those are the parts we need to effectively drop out of the force to get the field. And to do that, we just have to divide the force by that charge, Q1 or Q2, which is carried by the probe. And so the answer is C. This then is our prescription for measuring an electric field at any location. Now, we'll tend to abbreviate electric field as just E field. If you want to measure it at some place, say A, you place a charged probe particle at that location. You measure the electric force on the probe particle, and now you divide that electric force, which is a vector, by the charge of the probe particle. The result is a vector that we call the electric field vector. And notice in this example, because we know that the forces on Q1 and Q2 are proportional to the charges on Q1 and Q2, when we divide each of those by those charges, we get an answer that doesn't depend on which probe charge we used. We were able to reason that that was true because we knew that the force on our probe particle was determined by Coulomb's law. But what if we don't have 2 charges that we're talking about, a probe particle and some other charged particle? What if our source object is some other thing? Well, it doesn't matter. We still know that while the force may not be determined by Coulomb's law, it will still be proportional to the charge on the probe particle. And so dividing that force by the charge on the probe particle will still give us an electric field, which is independent of what probe particle we use. This is very important, and let me go through it in detail. By definition, the electric field has to only depend on the source object and the location where we are measuring the electric field. It must not depend in any way on the probe particle. That's the point. But students often get confused by this in the definition, because the definition explicitly includes the charge on the probe particle in the denominator there on the right side of the equation. The reason this happens is that this force is always proportional to the charge on the probe particle. And so when we carry out this division, there's a cancellation that occurs, and we always get an answer that's independent of the probe particle. This is very, very important. This is very, very important. This is so important that if you do not understand this in full detail, both that the E field must be independent of the charge on the probe particle and why it turns out to be independent, you really need to go back to part 1 of this lecture and re-watch it. Make sure you understand the answer to the question that I posed, If you get back to this point and still don't understand this, you should do other things. Perhaps you could go and read a textbook to get another explanation. Or, if you still don't understand, please, please, please come to me in person and work through it with me until you understand. This is so important that it's quite likely none of the rest of this course will make sense if you don't understand this point. This is not an exaggeration at all. You have to understand this. I'm going to finish up this video lecture by drawing your attention to the direction of the electric field. In all the examples I've done, I've used a positively charged probe particle. And so the E field ends up being in the same direction as the force on the probe particle. That makes sense from the definition. We're taking a force vector and we're dividing by a charge, which is just a positive scalar, and we know that when we divide a vector by a positive scalar, we get a new vector that is in the same direction. But note that if I replace that positive probe charge with a negative probe charge, then the force on it in this case must be in the opposite direction, right? It would be attracted to that source charge Q. And so now, because we know the electric field can't depend on the charge on the probe particle, that's telling us that the electric field is in the opposite direction to the force on the probe particle. Well, once again, from the definition, that makes sense. When you take that force and you divide it now by a negative charge, when you divide a vector by a negative scalar, you get a new vector that points in the opposite direction. Another way of understanding this is just by saying that if there's some location and you somehow know which way the electric field at that location points, then anytime a positive charge passes through that location, the electric force on it will be in the direction of the electric field. And anytime a negative charge passes through that location, the electric force on it will be in the opposite direction to the electric field.